Question 19, October 2020 paper. Electrode potential question. Standard electrode potentials for 4 redox systems are shown below. A student sets up a standard cell in the laboratory based on redox systems 3 and 4. So we are looking at this one and this one. Draw a labeled diagram, so it must be labeled, to show how the cell could be set up to measure its standard cell potential at 298 Kelvin. 298 Kelvin is a standard condition. Draw your 2 beakers. Now, with the silver, with this redox system 3, the silver itself will be used as an electrode because the silver is a metal that conducts electricity. And you're going to have a solution of silver ions, aqueous, and this is 1.0 moles per decimeter cubed. And we label the electrode silver solid. We'll shade that in. Now, this is connected to a voltmeter. And the other half cell, you see the other half cell, there are no metals in any side of the redox system. So when you are dealing with a mixture of ions, we need an electrode that will conduct the electricity but not chemically get involved. And what we use a platinum electrode. I'm using color here for illustrative purposes. In the exam, you only use a black pen. Please be mindful of that. And what you've got MnO4 minus for the redox system. Aqueous, you've got H plus, aqueous, and you've got Mn2 plus aqueous at 1.0 moles each. Okay, and this circuit is incomplete. What's going to complete it is the salt bridge that's in the middle. I don't know if you remember doing this practical. Until you put the salt bridge, you will not get a reading on that voltmeter. So you've got your salt bridge here. Three marks from complete circuit and voltmeter and salt bridge. So you get a mark for that. You got the silver Ag and Ag plus and 1 mole per decimeter cubed, and 1 mark for that. And it must be, oh, we didn't label this, platinum electrode. Platinum electrode, MnO4 minus, Mn2 plus, and H plus, all at 1 mole per decimeter cubed. 3 marks. Next question. A student warms a mixture of methanol with acidified potassium manganate solution. The student observes gas bubbles. Explain this observation in terms of electrode potential. So we want to explain it in terms of electrode potential and equilibria. Whenever we're dealing with equilibria, it's a case of, the equilibrium shifting left or right. Include overall equations. it's probably more than one. 4 marks. Let's see. Methanal and acidified dichromate. So you've got your acidified dichromate, potassium manganate. So you've got this acidified potassium manganate here, and it's reacting with methanal, which is here. Can you see that? Because what's going to happen is redox system 4 has an electrode potential more positive than the redox system 1. So let's write this down. The electrode potential system 4 is more positive than electrode potential of redox system, was it 2? 2. Now, as a result of this, the more positive the electrode potential, it has a tendency to gain electrons, and the more negative or the less positive, it has a tendency to lose electrons. So redox system 4 so for example, redox system 4 being more positive in its electrode potential, the equilibrium shifts to the right-hand side. Redox system 2 being more negative in its electrode potential, equilibrium shifts left. And so let's look at the overall equation for that. You got methanal and water. Methanal and water. Can you see, ladies and gentlemen, you've got, you've got 2 electrons here and 5 electrons here. So to balance these equations in terms of electrons, we're going to need to times this by 5 and multiply this by 2 to balance the electrons. So acidified dichromate and I can't remember what was that. Let's do one bit at a time. So MnO4 minus plus 8H plus plus, what was it, 5 electrons? Yep, 5 electrons. Plus, well, the electrons are going to cancel out. Let's react that with methanal, HCHO, HCHO, and that goes on to give you, let's put our big numbers. We're going to multiply this by 2, make that into a 16, and make this into a 5. That goes on to give you Mn2 plus 4H2O, and the methanal, oh, we've got water there as well. So methanal is reacting with some water as well. And we're going to times that by 5 as well. Oops, sorry if I'm going up and down too much. And that goes on to give you, so we're going to put a times that by 2 and times this by 2. And the methanal equation goes on to give you methanoic acid and 2H plus methanoic acid HCOOH and 2H plus, and the electrons. And to balance that, we put a 5 there. And what's 2 times 5 is 10. So we've got this equation so far. We need to do some cancelling out. You got 10H plus on the right-hand side. Let's get rid of that and make this into a 6 only, taking away the 10. You've got 5H2O. Let's get rid of that and make this into a 3. And that, I believe, is your overall equation. 2MnO4 minus 5 methanal, 6H plus, 2Mn2 plus, 5HCOOH, and 3H2O. That's correct. Now, the thing is, we've not explained the gas bubbles. Where have the gas bubbles come from? Can you see, ladies and gentlemen, that when you're in this reaction, this is going to produce some methanal. And methanal is also here as well. And so potassium, the acidified manganate solution, is also going to react with methanoic acid. Why? Because its redox system is more, has a, let me get my words right. Redox system 4 is more positive than the redox system 1. So that's going to react with methanoic acid, sorry, this one over here, and that's going to produce some CO2. That's where the bubbles are from. So what we're going to do, you know what, rather than keep going up and down, I'm going to write down the equation here. It's too much scrolling up and down. So what's happening, like before, MnO4 minus plus 8H plus, we're going to cancel out the electrons to give you Mn2 plus and 4H2O. Methanoic acid, you've got plus HCOOH, which goes on to give you 2H plus and CO2. And to balance, we multiply this by 2 and the other one by 5 to balance the electrons. 5, that becomes a 10, that becomes a 5. And we cancel out what's on both sides. 10H plus, get rid of that. And that's it. Let's check the mark scheme. 2MnO4 minus 5 methanoic acid, 6H on to give you 2Mn2 plus 5 CO2 and 8 H2O. Correct. And these are your 4 marks, 2, 3, and 4. And the last part of this question, methanoic acid can be used in a fuel cell. What's the difference between a standard electrochemical cell and a fuel cell? A fuel cell is where the substance chemically reacts with oxygen. So this question does come up, and let me just get the wording right for this. Bear with me, ladies and gentlemen. So a fuel cell uses from a reaction of a fuel with oxygen, chemical energy. Yeah, to create a voltage. That's the definition. So here can be used as a fuel cell. As with all fuel cells, the fuel is supplied at one electrode and the oxygen at the other electrode. The standard cell potential for this is 1.34. You've got the overall equation. Using the information in table 19.1, deduce the half equation for the reaction at the oxygen electrode and calculate the standard electrode potential for the oxygen half cell. So 19.1, we're going to use the first equation here, first redox system, and that's going to be flipped to the other side. So that will give you, so one of the half cells, yep. So look, you got HCOOH. This half cell will be this, gives you CO2 plus 2H plus 2 electrons. That's already been given to you. They want you to work out the other half cell, which goes on to give you the overall equation of HCOOH plus half O2 to give you H2O plus CO2. That means half O2 must be here. And because we need these two to cancel out, that must be on this side, plus 2H plus 2 electrons to give you H2O. Yep, that's our half equation there. This is the half equation we want. Just double check, does that cancel out? That cancels out, oops. That cancels out with this. That plus that goes on to give you that plus that. Yep, that works. So the highlighted is your half equation, and the standard electrode potential is going to be, remember, it's always the positive minus the negative value. In this case, the positive one is what we're trying to work out. The negative one is minus 0.11 minus 0.11, which gives you 1.34 volts. That means X would equal 1.23 volts. Yep, and the mark scheme supports that. That is the end of that question. I will see you tomorrow.